Hello, everyone. Well, thank you for staying up too late for some people. So I want to talk about shaping bipolar structures in Bornagain planetary nebulae. Well, at least that was the original title of my talk, but now I will only concentrate in our recent Alma observations of Abel 58 around this star, which is called V605 Aquila. My collaborators are here, Daniel Tafoya, students, and some of the students here, Martin Guerrero. Okay, I will not spend much time explaining what a Bornagain planetary nebulae is, so let me just remind that this is an exceptional thermonuclear runaway within an old planetary nebula. So what we have is an old, relatively expanded planetary nebula, and now we have the ejection of processed material inside it, which was caused by a very late thermal pulse. So at a certain point, the star goes back to the post-AGV or early post-AGV position in the HR diagram, reducing its effective temperature. And so this ejection of material produces a large quantity of carbon-rich dust. So what do we know about Abel 58? So we know that here on the upper right panel, I present an HSD image, which is you can see the outer hydrogen-rich nebula, and then this kind of like bipolar structure within its core, which is the hydrogen deficient. It was demonstrated like decades ago by several collaborators. I'm just showing here the spectrum from Martin Guerrero and Arturo Machado in '96. So you can see the spectrum of the outer nebula, which is the lower panel, has H alpha, hydrogen rich, and then the central knot it is hydrogen deficient. In 2011, Lau and collaborators suggested that the abundances are more consistent with nova-like eruption, or that is as a consequence of binary system at its heart. Infrared observations have shown that there's dust in this hydrogen deficient ejecta, something about 10 to the minus 5 solar masses. And Clayton in 2013, they described that this should be something like a toroidal disk and some bipolar ejection with a blue ejection expanding towards the northwest. So I want to remark that it is accepted that this object experienced a very late moment pulse 100 years ago. So in 2017, we obtained apex observations from this object, and we only detected CO with an expanded velocity of 80 kilometers per second. Sadly, we didn't have any special information on the spatial distribution. So we recently obtained Alma observations in July of this year. So here I am presenting you, in the upper panel is the optical image. In the bottom panels, you can see on the left, you see the continuum emission from Alma, detected from Alma. And then the contours are there then compared to the HSD emission in the right, which is the oxygen-3 emission. So you can see that the continuum is spatially correlated with the disk in this object, this hydrogen deficient ejecta. We detected emission from molecular emission from 3 molecules, CO, HCN, HC+, and more or less marginal detection from H13CN. You can see that the lines are very similar to that we detected in the apex observations. So finally, we got the first maps of molecular emission around Bornagain star, which here I am showing you in colors the maps of the different molecules, and then in contours in gray I show you the continuum emission, so the integrated continuum emission. So we see that it is somewhat like a barrel-like structure with the maximum of this emission towards the south in all of the emission lines. So the CO is the brightest and the best signal to noise line. So we produce this velocity structure using this line. You can see here we can map velocities something between -80 and 80 kilometers per second, similar as we obtained with the apex observations. And we can now see the velocity structure, the kinematics of this toroidal structure. So you see that the blue is expanded towards the southwest, and the red part is going towards the northeast, something like this. We try to assess the inclination of the disk. So we try to fit like a kind of like an ellipse to the maximum of the emission, and we estimate something about 33 degrees with respect to the plane of the sky. On the other hand, the optical observations, this has been known for some time. So the optical ejecta expands with velocities of about 220 kilometers per second. And the kinematics is backward. So the blue part is going, as I said before, towards the northeast, which is kind of like opposite to what we see in the molecular emission. But although this seems upward, a model of this emission should be something like a toroidal, a radially expanding toroidal or disk oriented with 33 degrees with respect to the plane of the sky, and then this bipolar optically emitting structures going further away from the disk. Actually, this is the projected velocities of this the disk, which is something about 145 kilometers per second, the molecular material. And then the optically emitting region, this bipolar ejecta expands something about 260 kilometers per second. These morphology is actually not different from other Bornagain planetary nebulae. In particular, I am comparing here our sketch or model we obtained for Abel 58 with HSD images for Abel 30 and Abel 78, which are thought to have experienced VLTP 1,000 years ago. So for Abel 30, which is the central panel, you clearly can see this kind of like a disrupted disk and some bipolar ejections, very well radially, not perpendicular to the disk. And then in the case of Abel 78 on the right panel, it's more difficult, but you can still see this beautiful clown tails distributions pointing radially towards the central stars, and this more diffuse bipolar jets or bipolar ejections. In a recent paper, we demonstrated that in Abel 78 in particular, the disk is mainly traced by hot amorphous carbon, which is, and we don't see any of that emission in the bipolar ejection. So it seems like chemically different, at least the dust has different species within the disk of these Bornagain objects. Just to comment on the dust temperatures and the mass, we actually estimated from the continuum, the dust mass, something about 1.2 10 to the -5, which is consistent with previous determination. And here, this figure, I'm showing you the same model that Clayton and the photometry they produced in 2013. And we just overplotted the Alma data here, which beautifully fits with this model. So this was very, very surprising and nicely, a nice result. Going further into this CO emission, we actually tried to, we discovered this pair of high velocity components, which are we show here with arrows. This is HCD, high velocity components, which have velocities of about 120 kilometers per second. So these, as you can see, they're aligned with the optically emitting ejecta. So what we have is something like this toroidal structure, these clumps very close to the toroidal structure, and then this optically emitting ejecta. I'll be back to that, but now let me just show you that we use the H12CN and the H13CN to estimate this carbon 12 to carbon 13 ratio of 5.6, which is consistent with the single star VLTP models from Miller-Bertolami, very, very close to single star evolution. But then again, I mean, we cannot ignore this extremely bipolar shape of the the nebula, the hydrogen deficient nebula, which definitely suggests a binary system at its core. So these high velocity components are very, very close to the star and 0.17 arc seconds. And we estimated a dynamical age of 20 years. So this is very, very young. So it seems like we are taking a look at the jet collimation from this Bornagain star. So we actually see material that was very recently ejected, still 100 years after the VLTP occurred. So this was very surprising. And so what we want to suggest is that the abundances are consistent with single cell evolution scenarios. So we propose that V605 experience a VLTP, not induced by a companion, but we think that it extended its outer layers and very likely entered into something like a common envelope phase with an unknown, yet unknown companion. And this is what is helping shaping the hydrogen deficient sector. So this is our idea of what is happening. So any comment is welcome in the discussion. So I just want to leave you with the final sketch of this, the ejecta. So thank you.
Thank you very much. I wonder if I could share the screen for a moment.
I have to stop my screen.
I just wanted to show you. I was a co-author on the Clayton et al. Paper, and I made this animation. This compares two Hubble images taken 18 years apart. And you can clearly see the expansion, more or less consistent with the description you just gave.
Wow, impressive.
Yeah, it's amazing.
We concluded that the central star was in here somewhere, and I think you agree with that as well.
Yes.
That you can see that nice dark band across this way. Anyway, I'll stop sharing. And if you want to put yours back up, you can. Other questions, comments? Anyone? Young people, old people?
What about the outer nebula? Can you show the outer part again? Tell me how they are oriented.
Yeah, so this seems to be, this is not a very nice image. I can show you. It's not here. So yeah, so the abundances of the outer nebula, there seems to be like very regular old planetary nebula. But it is apparently, it is also elliptical with the larger axis, the major axis on the north, kind of like a north-south direction, and the smaller, the minor axis on this, more or less on the same direction of this bipolar ejection. So it is kind of like not round at all.
And no evidence for a companion from photometry or whatever.
Not yet, no. So the star is very obscure behind this strong dust component. So I think in this Clayton paper, they presented broadband images centered on the carbon 4, trying to detect this wolfrate feature from the central star. And it's marginally detected. It's there, but no signs of the companion.
There's a question
sorry.
I was going to say there's a question in the chat from Miguel. I don't know if he wants to state his question.
Well, yeah, basically, thank you for such a nice talk, Jesus. Well, basically, I'm curious about the expansion velocity found in this object that is quite large. It seems to me it's comparable to the most extreme cases, such as Messel 3. Is this common among Bornagain planetary nebulae?
Yes, it's also what we observe in HUB1, AVIR 30, AVIR 78, something between 100 and 300 kilometers per second. So this is supposed to be an explosive a thermonuclear event on the surface of the star. So it is actually what we see in other objects.
Yeah, so it could serve to discriminate objects somehow. Maybe.
Between so the abundances are very specific. So these are, whenever you measure the abundances, and then you take into account the carbon you have in this extremely carbon-rich dust structure, you have abundances that fit very well with the VLTP scenario.
Okay, thank you.